Hi everybody, and welcome to the third part in this series on integrated broadband analog delay circuits. So we've so far looked at the motivation and background for our interest in analog continuous time broadband integrated delay circuits. We looked at some applications that were of interest: pipelining analog signal processing, FIR filtering, time interleaving, and we looked at their implementation using passive only elements. And we saw that one of the main drawbacks with the passive elements is the fact that they use relatively large components, especially the inductors and or transmission lines. Now, technology trends, fortunately, are affording us better and better metallization in the high layers of the interconnect. These have lower and lower series resistance, lower losses associated with them. At the same time, as applications proceed to higher frequencies, we're more and more interested in relatively short time delays, which allow passive delay lines to become more compact. So these trends tend to favor passive delay lines. However, they're still relatively large, and for some applications, all that on-die area is just going to be intolerable. So for that reason, we're going to now take a look at active implementations of analog continuous time broadband delay circuits, which we'll see can have smaller implementation area. So just a reminder that within our categorization of delay circuits, we're focused here on continuous time analog delays, and we're going to now focus on active implementations of continuous time broadband delays. Now we can further subdivide implementations here as those that rely on feedback amplifiers and those that do not rely only on amplifiers or buffers that operate open loop. The main trade-off here is that feedback affords us better linearity than we get with open loop amplifiers. That's because the feedback ensures that the active devices, the transistors themselves, only are exposed to relatively small signal swings. But feedback also tends to limit the bandwidth we can achieve. So because we're interested here in very broadband analog delay circuits, we're going to spend more time talking about those realized with open loop amplifiers. And there the main challenge is that they tend to be nonlinear. Now, the implementation of analog broadband delays with active circuits has a long history. Here's an example from ISSCC 1996, where active delay circuits were used to realize a 5-tap adaptive FIR filter. Each of the delay circuits itself was realized as shown here. It's essentially an Opamp-RC circuit that's synthesized to provide a Bessel Allpass response. The amplifiers themselves were realized with CMOS technology. Now, these feedback amplifiers here allow for higher linearity, again, because the op-amp differential inputs only see the virtual ground small swing. Another benefit of active RC implementations of filters like this is that the frequency response depends only on the passive component values. So we only need maybe light tuning of the values of R and or C to ensure a precise delay response. But I'd say that in this case, an application like this, that's an adaptive filter anyway, very precise implementation delay response may not be necessary anyway, since you're going to adjust and adapt the tap weights B0, B1, B2, and so on anyway. That can partially compensate for any non-idealities in the delay response. Again, the use of feedback here introduces loop stability requirements. We're going to target a certain phase margin around these local feedback loops that's going to limit the delay bandwidth and power trade-offs associated with the design of these amplifiers. And that's going to be particularly burdensome when we're pushing for very high signal bandwidths, pushing the technology up to its limits. So that makes this type of delay circuit implementation less attractive when we're going for very broadband circuits. So alternatively, we can realize active delay circuits just using open loop GMC circuits. Again, that has a very long history. This example was taken from the very same year ISSCC. The citation here is the JCC version of it. And in this case, it was a 7-tap FIR filter, again for magnetic storage, read channel. But in this case, each of the delay circuits was realized using bipolar programmable GMC integrators. those were used to synthesize a fourth order linear phase filter with 0.05 degree equal ripple error response. So we described that alongside Bessel responses at the start of this presentation. Now GMC circuits like these have no local feedback loops, so in general that's going to allow for a higher bandwidth than Opamp-RC circuits, but is going to give rise to lower linearity because the transconductors see a larger signal swing. Frequency response to these GMC circuits depend on both the transconductances, GM, and the capacitances, C. And so since the active circuits may exhibit significant process voltage temperature variations, GMC circuits may require more tuning than their Opamp-RC counterparts, but again, for a lot of applications, that's not going to be a showstopper. Tuning is going to be required anyway. Active circuits are relatively easily tuned, and we've got the adaptive tap weights of this FIR filter anyway to compensate for some of the non-idealities. So here are some examples of the simplest form of GMC delay circuits we can imagine. The first is a straightforward first order low pass delay circuit. There's essentially a low pass response formed by the RC time constant at the output of the transconductor here. The delay of this circuit is approximately equal to the time constant RC, and we'll see that delay at frequencies that are significantly below the 3 dB bandwidth of the circuit, which is simply 1 over RC. So we've got this delay bandwidth trade-off coming into play that we're now familiar with. If higher delays are required, we can simply cascade multiple stages in series as shown here. Each stage introduces another left half plane pole that's going to give us another 90 degrees of phase shift and an additional delay of RC. Now we mentioned before that GMC circuits' main limitation is going to be their limited linearity. If we focus on the static nonlinearity here, we can think of it as being determined by how constant the product GM times R, that's essentially the gain of this circuit, remains as the input voltage changes or swings. So we're going to get a certain gain for small input signals VI, but as VI increases, it's quite likely that the gain, static low frequency gain of this GMC circuit will start to saturate. And so this flattening of the gain is going to imply a static nonlinearity. Now, a slight modification to this GMC circuit would be to take the passive resistors R and replace them with diode-connected transconductors as shown here. The resistance that you see looking into this diode-connected transconductor is just 1 over GM, and so we can synthesize essentially the same delay response. It's just a series connection of first order low pass sections as we did above. We've got here only active elements for all components here except for the capacitor. So you might say, well, that makes the circuit more nonlinear. We've taken a passive resistor, which is inherently linear, and replaced it with an active circuit, which is going to have some nonlinearity associated with it. But the truth is that depending on the implementation of this transconductor, in fact, it can be more linear than its passive resistor counterpart. If it's suitably designed and matched in a way to this transconductor up here, then the nonlinearities associated with these two transconductors can cancel each other out and result in a more linear response overall. So this is going to be actually quite a useful structure in some cases. An example of that approach taken from our lab from 2008 is shown here. In this case, we're realizing a 6-tap FIR filter, and each of the delay circuits is in fact a series connection of 4 first-order low-pass delay circuits. Each of these is simply a differential pair acting as a transconductor going into what's called a symmetric load. This symmetric load circuit was first introduced a long time ago in 1993 by Maniatis in this classic JCC paper. And the idea here is that by combining parallel combination of a transistor and triode and a diode connected transistor, what you can have is a linearized small signal resistance here. And to understand that, we can imagine the current through each of those devices here on the y-axis plotted versus the drain source voltage across those transistors. Now for the device that's in triode, you see at first this linear triode IV characteristic, and then starting to curve and flatten out as it enters saturation for large values of EDS. On the other hand, for the diode connected transistor, we see first low values of current, then as VDS increases, we see the square law coming into play. So we have the opposite curvature in the IV characteristic of the diode connected transistor. So combining these two in parallel, you get the sum of these two currents, and you get a linearized IV response. So it's a way of using active circuits to get something that looks more like a passive resistor value. So that was useful in the works cited here because it affords better supply noise rejection. However, the nonlinearity of the input pair transconductance in fact looks more like what it did using a passive resistor R as the load. So the static nonlinearity is again limited by the nonlinearity in GM times R as a function of input level. Now in this paper here we've got 4 of them in series, so if each one provides a delay delta or a time constant delta at its output, then the total delay through each delay circuit is 4 times delta, but the 3 dB bandwidth is again limited to a fraction of the RC time, 1 over the RC time constant associated with each of those cells. So it's related to the delay here, 0.43 divided by the delay, and so that's far below the maximum bandwidth that's achievable for a 4th order response, and that's because we're simply using 4 left half plane real valued poles to realize the delay. They're not optimized in any way as they would be in, for example, a Bessel or equal ripple response. Now remember that when we only use left half plane poles in a delay circuit, we end up with a low pass magnitude response, and we only get 90 degrees phase shift from each pole. Instead, if we form an all pass transfer function by putting complementary right half plane zeros in the numerator of the response, we end up with twice as much phase shift and therefore twice as much delay with an all pass magnitude response. So here's a first order all pass active circuit that realizes a delay as shown here. So the assumption here is that the circuit is designed so that the product GM times R is equal to 1, and then in that case you've got a DC gain of 1 through this circuit and right half plane 0 providing an extra 90 degrees of phase shift. So a circuit just like this was used in a 7-tap FIR filter in this paper presented at ISSCC and JSSC in 2014. In a circuit like this, you've again got an active transconductor driving a passive resistive load. So the static linearity is again limited by how constant can you make this product over wide signal swings. And since the passive delay element will always have a resistance R, it's really all about the linearity of the transconductor GM. Now, a modification of this is introduced down below. So you'll notice here that there are fewer transconducting elements in the circuit. So this, the authors argue, is going to allow for lower noise because you've got fewer transistors contributing noise essentially to the circuit, and higher bandwidth because you've got fewer parasitic capacitances associated with the various nodes. But again, this circuit forms an all-pass response just like the one above with similar delay. So this circuit here was used in this paper at the VLSI Symposium in 2016 for a 5-tap FIR filter. Now another interesting feature of this circuit is that it makes use of no passive resistors. So instead, the static nonlinearity is determined by the product GM1 times 1 over GM2, because at very low frequencies the capacitor acts like an open circuit, so you've just got GM1 driving diode connected GM2. So if these transconductors are matched, it turns out that their nonlinearities will cancel, and that'll provide better linearity than what's offered using a passive resistor above. So a couple different ways to implement this GMC first order all-pass active delay circuit. One is simply using NMOS transistors as the constituent transconductors. So this common source transistor is serving as GM1, and this diode connected transistor up here is serving as GM2. So you can see the cancellation of the nonlinearity if you think about what happens as the input voltage Vi increases. As it does so, again, considering the static nonlinearity, we're thinking about low frequencies, so the capacitor sees an open circuit, and Vi goes up, VO will come down. As Vi goes up, we know that GM1 will increase, but VO comes down, GM2 will also increase. So the ratio of GM1 over GM2, which determines the low frequency gain of the circuit, will remain constant across relatively wide swings of Vi. Now, this is just sort of a very superficial first order analysis. There are second order effects that will still lead to nonlinearities, of course. So specifically, although the VGSs of transistors 1 and 2 here vary together, Vi goes up, VGS1 goes up, VO comes down, VGS2 also goes up. But on the other hand, their VDSs vary in opposite directions. So as VO comes down, VDS1 decreases, VDS2 increases. And so this is a second order effect that will cause their GMs to move in opposite directions and hurt the linearity, ultimately limit the linearity of the circuit. At the same time, if we think about what happens at high frequencies, the capacitor C shorts these two nodes together, Vi and VO. So at high frequencies, these two nodes move together. Vi goes up, VO also goes up. And then we lose the nonlinearity cancellation that we talked about. The circuit's high frequency linearity is also limited. So the paper presented at the VLSI Symposium in 2016 instead used perfectly matched transconductors, full CMOS transconductors, sometimes called NAUDA transconductors, as each of the constituent GM1 and GM2s. GM2 diode connected here. So in this case, you've got improved linearity because both transconductors see the same swings. On the other hand, as compared with the example on the left, we can expect the bandwidth to suffer somewhat because, again, you've got just more parasitics associated with the various nodes in the circuit. Specifically, you're making use of PMOS transistors as transconductors, which may have a larger gate area for the same value of transconductance because of the lower mobility of holes compared to electrons. Now here's a slightly different approach to realizing this same GMC all-pass first order delay, but with higher linearity. So in this case, the transconductances are being provided by passive resistors, as passive devices are going to be a more linear transconductance than a transistor, of course. So what's shown here is that with source degeneration, the transconductance GM1 will be dominated by 1 over the value of this resistor rather than the small signal nonlinear transconductance of the MOSFET itself. So that's going to tend to linearize the transconductance GM1. At the same time, we provide a linear load resistor up here. So that's serving as GM2. So now you've got a static linearity that's determined by the ratio of these resistors rather than active transistor transconductances. So that's going to offer better linearity. The downside here is that you've got perhaps some headroom issues to allow for the DC voltage drops across these resistors that arise because of the bias current that's needed to keep this transistor active. A variation of this circuit was presented at the RFIC Symposium in 2004, except in that paper, the transistor here was actually a bipolar device, but the same premises and trade-offs were at play there. So in this example here, however, you've still got some variations and nonlinearities that arise because you've still got an active device here that's seeing some VGS swings and also some VDS swings. So in fact, as VI goes up, this source node also moves up, but VO will move down. So VDS is changing quite a bit as VI swings, and that's going to give rise to some nonlinearity in this circuit. So to try to mitigate that, this variation here on the right introduces a cascode device. A telescopic cascode device helps keep VDS more constant in this bottom transistor and therefore reduces the nonlinearity introduced by VDS variations on this transistor. So here is a sort of more complex variation of that last circuit that was presented. This was from our lab and appeared in IEEE solid-state circuits letters in 2020. It's quite a complex circuit. There's a lot more going on than we showed on the simplified single-ended version on the last slide, so we're just going to walk through it one step at a time. So here is a fully differential version of the active delay circuit that was shown on the last slide. This appeared in solid-state circuits letters in 2020 from our lab, and you'll see the input pair are these NMOS transistors here, and they're source degenerated, just as shown on the last slide for better linearity. The cascode devices here are PMOS devices, so this forms a folded cascode that allows for a lower supply voltage than the telescopic cascode that was illustrated on the last slide. The drawback is that it introduces a little extra noise because of the extra bias current that's required in the current sources. So a challenge with GMC circuits, of course, is that the pole, zero, and gain may all vary significantly over process voltage and temperature due to transistor parameter variations. So in this circuit, some tunability is provided via these two resistors here. The tunability in this resistor allows us to control the location of the zero. This is similar to the lead compensation resistor in a two-stage op-amp, but in that case, the value of the resistor is chosen so that the zero wraps all the way around from the right half plane to the left half plane, thereby providing a phase lead and some extra phase shift. In this case, the value of the resistor is just tuned to fine-tune the location of the zero in the right half plane and provide us that extra 90 degrees phase lag. But we're going for the all-pass response so that the zero location should mirror that of the pole location. The load resistor here is also made adjustable. That allows us to adjust the frequency of the dominant pole and the gain of the circuit. And again, we can do that to try and achieve a nice all-pass response. So an interesting feature of this active delay cell is the gain boosting amplifier, here highlighted in blue. And its primary purpose, as usual with gain boosting amplifiers, is to limit the swing on this cascode node here and thereby limit the nonlinearities introduced by these transistors. Now for a very broadband, high-speed delay circuit here, one might imagine that the requirement on this gain boosting amplifier is quite tough. It would require, you might imagine, a very high gain bandwidth product. But in this case, it's actually not quite true. Essentially, the finite gain bandwidth product of this gain boosting loop introduces an additional pole zero pair into the response of the circuit. And by placing that pole zero pair within our bandwidth of interest, we can actually get some additional phase shift from that gain boosting loop and provide a higher delay bandwidth product for the circuit overall. So this means not only do we not have to provide a very high gain bandwidth product in this gain boosting amplifier, it's actually beneficial that it not have too high a gain bandwidth product. Finally, source followers buffer the differential outputs here. These are PMOS source followers, and you'll notice that there's an auxiliary source follower here that's being used to drive the body terminal of the main source follower transistor. This is a scaled down replica of the main branch here, and that helps mitigate nonlinearity introduced by body effect on this transistor. Also shown in gray here is a common mode feedback loop, that regulates the main bias current up here. Here are some simulation results of the circuit in a 28 nanometer technology. This version of the circuit was designed to have a delay of about 80 picoseconds with a bandwidth of about 3 gigahertz. And you'll see in the simulation results over here on the right that it has a relatively constant magnitude response of 1 volt per volt up to right around 3 gigahertz. And shown here in green is the group delay of the circuit, again staying relatively constant around 80 picoseconds up to 3 gigahertz. And just for comparison, we show here the group delay that we would expect from an ideal first order all-pass response. And so this is just to illustrate that the circuit is achieving a wider bandwidth than what would be achievable with a first order all-pass response. So that indicates that this gain boosting amplifier is actually extending the bandwidth of the circuit with the additional pole zero pair it's introducing. A prototype implementation of the delay circuit is shown here in the top right. The delay circuits are actually visible if you just zoom in on this area here. So they're quite tiny, especially by comparison to a passive delay network made of inductors and capacitors that would be designed to achieve the same amount of delay. The drawback, of course, is that it has limited linearity, especially compared to an all-passive circuit for delay. Measurements on the left here in red are compared with extracted simulation results in black, and also compared with an ideal second order all delay response with the dashed line. So you can see that the delay is increased by about 10% compared to the simulations in the last slide due to the addition of the parasitic capacitances in the circuit, but the bandwidth achieved is in excess of 3 gigahertz, which is great. And you've got some nice transient waveforms here illustrating the constant delay of the circuit across the bandwidth of interest. So the point of this paper was to make use of the delay circuits in a continuous time pipeline analog to digital converter, and that's illustrated here in this block diagram. You can see the input is delayed by the active delay circuits along the bottom here, and those delays are matched to the delays of the comparators and associated logic in each stage of the pipeline, and also to the delays in the clock path up here in the top. So this three-stage pipeline A to D realizes a 5-bit converter at 7 gigasamples per second. Now, because the input is only loaded by one of these relatively small active delay circuits, the input capacitance of the overall continuous time pipeline A to D is only 15 femtofarads, which is much less than what would be typical for a 5-bit A to D at this speed in this technology, which would normally require a full flash A to D. Now you can imagine that once you're providing the input to an analog delay line like this, you're already creating multiple delayed copies of the input waveform. You can reuse that delay line to time interleave the analog to digital conversion. And so that would kind of amortize any power or area overhead associated with the delay line over many A to Ds and allow you to achieve a much higher overall sampling rate. In fact, in a case like this, you'd be amortizing the cost of the delay line so much that you might be able to afford the passive delay line with its large area. And that would then allow you to achieve even higher bandwidth, lower noise, and better linearity. So I think this is an interesting potential direction for future work in this area. I'd just like to conclude by summarizing the main points from the overall presentation. We talked about how analog delay circuits are really fundamental building blocks. It can be useful for many signal processing functions, including filtering, pipelining, and time interleaving. We also saw that analog delay circuit implementations exhibit quite fundamental trade-offs between delay, bandwidth, area, and power consumption, since those are related to the order of the delay response that we're after. Now, these trade-offs play out differently depending on whether you're implementing the circuit with passive or active components. In general, integrated circuit implementations become more feasible when the delay time you're trying to realize becomes shorter and the bandwidths associated become higher. And so I think it's interesting that technology trends have really paved the way for increased use of these analog delay circuits. Now, with advanced technologies, we're targeting very broadband applications that require very high speed, but those speeds are being supported by aggressively scaled CMOS technologies. And because we're processing higher bandwidth signals, it's really shorter delay times that we're after, which are easier to implement on chip. At the same time, CMOS technology scaling has afforded us a lot of low resistance metal layers in the technology, and that benefit the implementation of integrated inductors, which are often playing an important role in passive delay circuits. So in the final part of this presentation, we reviewed both active and passive circuit implementation of analog delays. We saw that passive delays afford the potential for better linearity, lower power consumption, and higher bandwidth than active circuits, but can consume very large area on chip. Active delay circuit implementations are smaller in area, and that's particularly important for long delay times when the area required for passive implementation becomes prohibitive. So I'd just like to finish up by acknowledging the work of the many graduate students from my lab over the years whose work was summarized here. Thanks very much, guys, and thanks everybody for watching.